Hi everyone. We want to prove that the following functions are continuous at a given value of x. And we're going to use our three conditions for continuity at a point. So our first function, g of x, is the absolute value of 4 minus x, and we're interested in proving that this function is continuous at 4, using our calculus knowledge. So you may have an instinct about this function from your college algebra knowledge. You might be thinking this absolute value function will be a V-shaped graph, and visualizing that graph, you probably are thinking, yes, this should be continuous. But we want to prove with our calculus knowledge that indeed we know for sure it's continuous at 4. So our first condition for continuity is that the function has to be defined at the given x value. So that means we need to show that g of 4 is defined. So g of 4 would be the absolute value of 4 minus 4, which is 0. So because we did get a value, an output, we can say, yes, the first condition has been met. Second condition for continuity at a point is that the limit must exist as x approaches 4. So we need to figure out what the value of the limit is as x approaches 4 of the absolute value of 4 minus x. So utilizing our knowledge from earlier in this class, we have to analyze the absolute value. So we know that absolute value functions can be rewritten as piecewise functions. So we're going to start by rewriting the absolute value of 4 minus x as a piecewise function. And we know that that would be equal to the opposite of 4 minus x if 4 minus x is less than 0. But it will be equal to just 4 minus x if 4 minus x is greater than or equal to 0. So you might need to go back and review some of your notes previously on absolute value to remember exactly how this works if it's not fresh in your head. So now looking at these inequalities, we need to go ahead and solve, and you could either, subtract 4 and divide by a negative 1, but rather I'm going to choose just to add x to the other side. So I would have 4 is less than x, which is the same as x is greater than 4. And then my second condition here, if I add x, will give me 4 is greater than or equal to x, which is equivalent to x is less than or equal to 4. So going back to this limit, we need to look at the left and right hand limits and see if they are the same. So we'll look at the limit as x approaches 4 from the left. Now, if we're approaching 4 from the left, we are analyzing values that are smaller than 4. So looking at our piecewise function, we know that if x is less than or equal to 4, then we are utilizing 4 minus x as our function. So we can replace the absolute value of 4 minus x with just the quantity 4 minus x when we're looking at the left-hand limit. That's going to allow us to do our direct substitution, 4 minus 4, which gives us a left-hand limit of 0. Now the right-hand limit is next, the limit as x approaches 4 from the right. And again, if we look at our piecewise function, if we're analyzing the limit as x approaches 4 from the right, then we're looking for values of x that are larger than 4. And if x is greater than 4, then we are on this side of our piecewise function, which is the opposite of the quantity 4 minus x. So this will be the opposite of the quantity 4 minus x. You can think of it as replacing the absolute value with the appropriate piece. And then we can do direct substitution at this point. So the opposite of 4 minus 4, which indeed is still going to give us 0. So what we have just proven with this second condition here is that the left-hand limit is equal to 0 and the right-hand limit is also equal to 0. Therefore, the limit does indeed exist. So the limit as x approaches 4 of the absolute value of 4 minus x is equal to 0. So the second condition has been met. And finally, the third condition for continuity at a point is that the value of the limit is indeed the same as the function value. In other words, we have shown that g of 4 is indeed equal to the value of the limit as x approaches 4 in this case. Because g of 4 was equal to 0 in condition 1, and the value of the limit as x approaches 4 was also equal to 0. So therefore, condition 1 and condition 2 are the same. They're equal. So the third condition has been met. So we can write a summary statement if you want to use the 3 dots in the triangle formation to represent therefore. Now you can say, therefore, g of x is continuous at x equals 4. And we have proven that using our calculus knowledge. Our second function is a piecewise function, and we are looking to determine if this function is continuous at x equals 1 using calculus. So again, let's go back to our 3 conditions for continuity at a point. So the first condition is the function has to be defined at the given value. So in this case, h of 1 needs to be defined. Now, since this is a piecewise function, we need to look at where x can equal 1. And you'll see that x is greater than or equal to 1 here in the bottom function. So if x is equal to 1, then we are substituting 1 into the bottom piece. In other words, into x plus 1. So h of 1 will be 1 plus 1, which is 2. And yes, the first condition has been met. The function is defined. The second condition is that the limit must exist. And since this is a piecewise function, we will need to look at the left and the right hand limits and be sure that they are equal to one another. So let's start with the limit as x approaches 1 from the left. Now, approaching 1 from the left means we're looking at values smaller than 1. And if x is less than 1, then we are utilizing the function x cubed minus 2. So the left-hand limit will be the limit of x cubed minus 2. And since that's a polynomial, we can go ahead and do our direct substitution. So we will have 1 cubed minus 2. In other words, 1 minus 2, which would be negative 1. Now the right-hand limit is the limit as x approaches 1 from the right. But again, as we saw earlier, if x is approaching 1 from the right, that means we're looking at values larger than 1. That means we're on the bottom piece of this function, so we would be analyzing x plus 1. So the right-hand limit will be the limit of x plus 1. We can do direct substitution there also. That'll be 1 plus 1, which is 2. But notice what we have found here. The left-hand limit does not equal the right-hand limit. So because the left-hand and right-hand limits are different, that tells us that the limit of our function h of x as x approaches 1, that limit does not exist. The left and right hand limits are not the same. So this means that the second condition for continuity has failed. So we can now conclude, therefore, if you want to use the 3 dots in the triangle formation, therefore, h of x is not continuous at x equals 1. It failed the second condition for continuity at x equals 1. Therefore, this is not a continuous function at x equals 1.